Welcome to my Switching, Routing, and Wireless Essentials course. This should be the CCNA version 7 curriculum. This is the second of 3 courses. Module 8, SLAAC and DHCPv6. So, we're going to be talking about IPv6, global unicast addresses, what SLAAC is, how it relates to address allocation, DHCPv6, and how to configure DHCP6. So if you haven't figured out SLAAC and DHCPv6, all specifically are dealing with how we obtain automatically IPv6 information. So let's go ahead and jump right on in. IPv6, the GUA assignment. GUA is global unicast addresses. You can do this one of two ways. You can do it dynamically or statically. So if we're dealing with a Windows host, again, we go to network properties, IPv6, and there you go. However, manually entering GUI address information can be very time consuming. And with IPv6, if you've watched me in my lab videos, you'll see that it's a slow process. So, most Windows hosts are enabled dynamically. That way you can get your own GUA address via its configuration. So, in previous videos we talked about GUA versus link local. Link local are going to be FE80 based addresses. Well, those are addresses that still play a huge role of how everything functions, because a lot of communication still happens via the link local address. So, if automatic IPv6 addressing is selected, the host will use ICMP, the version 6 of ICMP, and it will do a router advertisement message to help its auto configuration. So essentially what ends up happening is the IPv6 link local address is automatically created by the host when it boots up. Once the NIC becomes active, it gets a link local address. The interface did not create a GUA address because the network segment did not have a router to provide the host details. So here we have FE80 : FB : 1B54:83 yada 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 %21. The percent and the number at the end of the link local address is known as the zone ID or the scope ID, and this is used by the OS to associate a link local address with a specific interface. For those that have asked, DHCPv6 is defined by an RFC that is defined by 3315. So most of what we're focusing today is how we do address assignments, not just link local address assignments. So GUA is done in 2 major ways. Again, we're talking dynamic GUA assignments. We have stateless and we have stateful. Alright, so a common question is, what's the difference? Stateless, there is no device tracking of the IPv6 assignments. With stateful, there is a DHCP server that is managing the assignments of IPv6 addresses. What's really interesting is, with all of the QA that these slides go through, assignment owed IPv6 instead of. But little things. Anyways, so with stateless, we have 2 main types. Stateless deals with SLAAC and SLAAC with DHCP. So SLAAC is what we're going to be talking about coming up. With stateful, we have just a straight DHCP server, which is stateful. We want something that's going to track it. SLAAC only basically will send router advertisement messages providing all of the IPv6 address information. With SLAAC with DHCP, the router advertisement message provides IPv6 configuration information to the host that will inform them to contact a stateless DHCP server for the additional configuration. Default gateway and DNS, things like that, that can go to all hosts, aren't really needing to be trackable. With stateful, with DHCPv6, the router advertisement message informs the host to contact a stateful DHCPv6 server or some type of DHCP enabled device for all IPv6 configuration except the default gateway. That can be automatically assigned. So when we're dealing with IPv6 addresses for global unicast based addresses, we have to look at three main message flags. The way that this functions is we have an A flag, O flag, and M flag. And these are part of the ICMPv6 RA messages, RA router advertisements. So the A flag is the address auto configuration flag that signifies the use of SLAAC. SLAAC is the stateless address auto configuration used to create IPv6. The O flag is the other configuration flag. This basically means the additional information is available from a stateless DHCP server. So if we're talking stateless, A and O. If we're talking stateful, we're using an M flag. And you'll notice at the bottom, the M flag is the managed address configuration flag to use stateful DHCP. So depending on the type of address, we'll either get an A, an AO, or an M. So that lets us get into a little bit better understanding of how the addresses are actually assigned. So we're going to be looking at SLAAC first. Again, stateless address auto configuration. Alright, so let's go and do a SLAAC overview. So not every network address has to come from an IP or from a DHCPv6 server. The interesting part here is centralizing address management isn't always a good thing. So with SLAAC, we don't have to worry about a centralized device actually accessing and managing them. SLAAC is stateless, which means there is no server that maintains the information. SLAAC will send periodic ICMPv6 RA messages. This is by default every 200 seconds, providing addresses and other configuration to hosts so they can auto-configure their addresses based off of that router advertisement. Hosts can also send router solicitation RS messages requesting RAs. SLAAC can be deployed with SLAAC only, or it can be in conjunction with SLAAC with DHCP. SLAAC with DHCP, SLAAC still does a lot of it, but additional information can be pulled from that DHCP server. The server in this regard is not maintaining address information. So how do we enable SLAAC? You go to whatever interface you want to, and you can do a link local address. You can do a GUI and / prefix or subnet address, and you can also look at all IPv6 node addresses. Those are the three main types of addresses that are attached to a interface. What's interesting is, again, here we can see we get more than one type of address. With IPv4, you had your main IP address, but you also had different multicast groups that the interfaces could be associated with. Here we have multiple addresses, just different types of addresses. The second you allow for IPv6 unicast routing, you should start seeing that IPv6 multicast groups start sending RAs. And the RAs will contain the SLAAC information. So enabling SLAAC, basically show IPv6 interface, will allow us to look at the groups that the interface is attached to, even if we've not currently set up an address just yet. So let's look at SLAAC only. Here we have an A flag set to 1. So the A flag will inform the client to use IPv6 global unicast address prefix in the router advertisement, and basically they dynamically create its own interface ID. The O and M flag are set to 0, and this will inform the client to also use the additional information in the router advertisements, like DNS server, MPU, and the default gateway information to configure itself. You'll notice the default gateway will probably be set to a link local address. and that will be the link local address of R1. That's what's coming in the router advertisements. If you want to set the global unicast address for the default gateway, that's not going to probably come from a SLAAC address. That's going to be coming from a SLAAC with DHCP or DHCP. So essentially what ends up happening is a PC comes online, it will send a router solicitation, or the router will send the router advertisements every 200 seconds. When the router receives an RS message, it then again populates an RA to be sent out. IPv6 is enabling hosts wishing to obtain the address and will send the router solicitation to the multicast address. That way the router will pick it up and respond. So the multicast address for all routers in IPv6 is FF02::2. That's a special address that router solicitation messages will be sent to. That's a multicast address grouping all IPv6 enabled routers. So the PC boots, it will send that multicast message out. The router should receive and then respond. And it will send it to the FF02::1, which is an IPv6 all-node multicast address. So now we just learned that FF02::2 is all routers. FF02::1 is all nodes. So the PC will accept the router advertisement and then create its interface. So using SLAAC, a host will acquire its 64-bit subnet information from the router advertisement and will have to generate the remaining 64 bits of the interface identifier. This is done two ways. Randomly generated, this is normally done used in Windows 10, or a EUI64. What's interesting is the EUI64 basically will create an interface using the MAC address, and we're going to talk about a little bit more of the EUI64 method a little bit later. Because there was concerns about with privacy, this is basically because the Ethernet MAC address of the host is used by the EUI64 to create that interface ID. So there are some weird oddities with the EUI64 because it uses a physical address. Windows, Linux, and Mac allow for the user to modify the generation of the interface ID, either to create randomly or to use the EUI64. So, with SLAAC, hosts may use DAD, duplicate address detection process, to ensure that their address is unique. Just how we had Windows 4 using DAD, we can use DAD in IPv6, but instead IPv6 will be using a neighbor solicitation. That's going to be part of CCNP, and this message is basically constructed a solicited node multicast address containing the last 24 bits of the IPv6 address to ensure that no one else has. So if no other devices respond with the neighbor advertisement message, then the address is virtually generated to be guaranteed to be unique. So it will be generated, it will be checked, and then if no one says they have the duplicate address, then you know it is unique. If an NA is received by a host, then the address is not unique, and essentially the host will generate a new one. That is not really required because a 64-bit interface provides 18 quintillion possibilities, and likelihood of overlap is actually extremely low. So, that's kind of what it is. Questions, concerns, please reach out. Thank you.